Hi everyone, I am Christian Alzalbilas Piñas, and today I am gonna discuss about my final exam in computer architecture. So the first question, we have what type of locations can hold source and destination operands? Then, what is the difference between arithmetic shift and logical shift? So, the type of location that can hold source and destination operands in instruction sets depends on the specific architecture and design of the computer system. Operands are typically stored in registers, memory locations, and immediate values that are part of the instruction itself. Memory locations store data for longer term or more intensive use, while registers are frequently used for quicker access to operands. So, the difference between arithmetic shift and logical shift lies in how they handle the shifted bits. So, in arithmetic shift, when shifting right in an arithmetic shift, the sign bit, the leftmost bit of the original number, is inserted into the empty bit positions on the left. The empty bit positions on the right are typically filled with zeros when shifting left. Arithmetic shift are frequently applied to operations involving signed integers. So while logical shift, when shifting left or right, zeros are placed in the empty bit positions. Bit manipulations and unsigned integer operations frequently make use of logical shift. So the next question is, what is the difference between post-indexing and pre-indexing? Then B is, what are the advantages and disadvantages of a variable length instruction format? So in the pre-indexing, the effective address is determined prior to the operand being fetched in pre-indexing. Before reaching the memory address, the index or offset is added to the base address. The operand is directly accessed using the updated address. While post-indexing, the effective address is determined in post-indexing subsequently to the operand's retrieval. After the operand is fetched, the base address is used to access the memory location, and the index or offset is then added or subtracted from it. So, advantages and disadvantages of a variable length instruction format. So the advantages, we have code density. Higher code density is achieved by using variable length instruction formats, which enable more compact instruction encoding. This may result in better cache utilization and lower memory requirements. The next is flexibility. Variable length formats enable more efficient representation of various types of instructions with different operand sizes by offering flexibility in terms of instruction length. So, the disadvantages, we have complexity. Variable length instruction formats can make decoding instructions more difficult and necessitate the use of more advanced decoding logic in the processor. Then we have variable fetch time. Instruction fetching and pipelining strategies in the processor may become more complex when fetching instructions with variable lengths, as they may take varying amounts of time. Then, difficulty in parallel execution. Variable length formats can make it difficult to execute instructions in parallel, which can affect the processor's overall performance. So, in processor structure and function. Letter A. What general roles are performed by processor registers? Then B. Why is a two-stage instruction pipeline unlikely to cut the instruction cycle time in half compared with the use of no pipeline? So in letter A, the processor registers play several crucial roles in a computer system. We have data storage. The data that the CPU is currently processing is stored in register. They offer quick access to operands for logical and arithmetic operations. The next one is address storage. Some registers store memory addresses. facilitating memory access during load and store operations. Then instruction storage. The instruction storage or the instruction register or IR holds the current instruction being executed, and the program counter or the PC keeps track on the address of the next instruction. Then the temporary storage. Registers act as temporary storage for intermediate results during computations. So the control information, we have certain registers store control information related to the execution of instructions, flags, and status bits. Then operand storage. Registers hold operands for instructions, allowing for efficient data manipulation. Then the letter B, the execution time will generally be longer than the fetch time. So here's why a two-stage instruction pipeline is unlikely to cut the instruction cycle time in half, compared with the use of no pipeline. So the execution time will generally be longer than the fetch time. Thus, the fetch stage must wait until it receives the next instruction address from the execution. One is we have reduced instruction set computers or RISC. A. If a circular register buffer is used to handle local variables for nested procedures, describe two approaches for handling global variables. So, when using a circular register buffer for handling local variables in nested procedures, global variables can be managed through a couple of approaches. We have direct access. So, reserve specific registers or a portion of the register file for holding global variables. Global variables are directly accessed from these registers without going through the circular register buffer. This approach ensures that global variables have dedicated storage locations. Then the next one we have memory access. Global variables can be retrieved directly from memory if they are not assigned to any specific registers. A global variable is loaded from memory into a register so that it can be processed when needed. Although it might be less effective than direct access and require additional memory access, this method gives registers greater flexibility in their use. Characteristics of a RISC instruction set architecture. So, simplicity. RISC architectures are designed with a simplified and reduced set of instructions, focusing on a basic operations that can be executed in a single clock cycle. Fixed length instructions. Instructions in a RISC architecture typically have a fixed length, simplifying the instruction fetch and decode stages of the pipeline. So we have load or store architecture. A load or store architecture is commonly used in RISC architectures in which data is only transferred between registers and memory during operations. Data from registers is used to conduct arithmetic operations. Then register operations. RISC instructions primarily involve operations between registers rather than between memory and registers. This minimizes memory access and emphasizes the use of a large register file. Single cycle execution. When possible, instructions are made to complete in a single clock cycle, which promotes effective pipelining and possibly faster clock rates. Then, hardwired control unit. So, RISC processors commonly use a hardwired control unit, which simplifies the control logic and contributes to faster instruction execution. Level parallelism and superscalar processors. So, what is the difference between the superscalar and superpipelined approaches? Then, what is register renaming and what is its purpose? So, the difference between superscalar and superpipeline approach. Superscalar approach has several execution units. It can issue and carry out several instructions simultaneously in a single clock cycle. By taking use of instruction level parallelism, it can simultaneously send several instructions to several function units. While super pipeline approach is divided into more stages compared to a traditional pipeline, each stage handles a specific phase of instructions execution. Super pipelining aims to increase the clock frequency and improve throughput by breaking down the execution process into smaller, more specialized stages. So essentially, a superscalar and super pipeline processors both seek to increase performance. However, superscalar processors accomplish this through the use of multiple execution units, whereas super pipeline processors accomplish this by segmenting the execution process into several pipeline stages. Then B, the register renaming and its purpose. So the register renaming is a technique used in a modern processors to minimize misleading data dependencies and promote instruction-level parallelism. It entails translating architectural registers, those that the programmer can see, into physical registers, which are the processor's real storage location. So its purpose is to overcoming data hazards. More precisely, register data hazards is the main goal of register renaming. In a pipeline, when instructions are run out of sequence or in parallel, there may be dependencies between instructions that could result in hazards such as read after write or RAW hazards. Registers renaming reduces this risk by offering a greater number of physical registers, enabling separate execution of different instructions that share an architectural register. So by using register renaming, the processor can execute instructions more efficiently, reducing pipeline stalls and improving overall performance. It enables greater exploitation of instruction level parallelism by allowing instructions with dependencies to be executed concurrently.